Hi guys, this is going to be a video to help you study for doing proofs in logic, specifically in truth functional logic. Um, this is made specifically for you students at the University of Illinois Chicago. I found that there was not a lot of materials online for the particular textbook, the particular system that we use. And there's also about a million different ways that people teach logic because it's in so many different fields. So I'm hoping if you're a student at UIC, this is good for you. And if you're not a student at UIC and you're learning logic, you might have more rules than we have. And so hopefully, if you see this, then maybe some of the ways we do things, it'll be easier for you if you can throw a rule that maybe we don't have at the particular proof we're doing. So what I'm going to try to do here is do 4 videos. I want to introduce everybody to the rules in case you missed them in class or something like that, or just need a review. So I'm going to state all the rules. We're going to do a few basic problems with these rules. That way you can just practice applying them. Next time we're going to cover conditional proofs. That's when you start using subproofs and making assumptions and all that stuff. And then in the third one, I plan on doing proof by contradiction, so you can practice that a little bit. And then I want to make a 4th one with some harder problems, like proving De Morgan's laws and things like that in our system, which turns out to be surprisingly tedious and hard. But those problems, if you can get all the way there and you can do them, then you'll probably be ready for anything in this course. Okay, so I'm going to list out all the rules. If you haven't seen these symbols before, then you will know very quickly from context probably what they mean. But it's good to have all these down on a sheet of paper before you start practicing problems. So go ahead and write all these down on one sheet of paper before we get going. Okay, so the first one is and introduction. How this works is if you have 2 sentences, A and B, separately, great, you can conclude A and B. So up here is what you're given. This is the information you're given. This is what you can conclude. Okay, so all the rules are going to look like this. There's going to be some given information up here. What you can conclude is down here. Okay, and this one is going to be called and introduction. So I'm going to write that down. And introduction. Okay, there's another and rule called and elimination. That's this one. If you're given A and B, guess what? You know A. And you know something else too, B, right? You know both of these separately because that's what and means, okay? So going from here to here is called and elimination, like this, okay? So we got two rules so far. These are our 2 and rules. Let's now look at the or rules. First one, we can do or elimination. So let's say you got A or B. And let's say you find out not A. This means that at least one of them has to be true, right? This tells you that it's not A, so from this you can conclude B. This is called or elimination. And it works the other way around too. If you get not B, great, you can conclude A. Okay, so this is or elimination. The other or rule that we have is or introduction. And sometimes this trips people up learning this for the first time. So let's say you're given a sentence X. From just this sentence, you can add any other sentence you want with A. Did I say X? I meant A if I said X. You can add any other sentence you want with an or symbol. Why can you do that? Well, this or symbol, for this sentence to be true, at least one of these sentences has to be true, right? So if you already know A is true, this or statement doesn't care about what B is doing. It's true by itself just because A is true, okay? So this one ends up getting used a lot, even though it's a little bit tricky to learn. So this is called or introduction. Okay. Next thing we got is arrow elimination. So let's say you're giving A implies B, and you're given A. From this, you can conclude B. So A implies B, you get A, that means you know B. This is called arrow elimination. Okay? Next is biconditional elimination. And it works exactly the same way. You can get A. If you have A, you can get B. Or you can do the other way around in a biconditional. If you get B, you can conclude A as well. This does not apply for the normal arrow. This thing kind of is like just like an arrow, but it goes both ways, okay? So this is called biconditional elimination. Okay, let's see what else we gotta do. Okay, so this is going to be a lot of the simpler rules. I don't think there's one that I haven't covered that involves a subproof. So this is the simple deductions you can make in logic. Okay, now we're going to cover some special ones that involve assumptions. So this is usually a difficult point for people to learn, including myself. But in some cases, to prove things, you're going to have to make an assumption. And the first example of that is going to be arrow introduction. Okay? So we found out in arrow elimination how to use an arrow statement, but now how do we want to prove an arrow statement? What you can do is assume A, for example. Okay, this is an assumption. Assumption. And this vertical line tells us when that assumption is running. So whenever you start an assumption, you want to start a vertical line as well. And everything that happens in here, inside the proof, is under the assumption of A. That's very important, and you'll get used to it over time. But from this, we can do a couple steps using those simple rules that we just put down. And let's say you get B inside this little assumption world in here. That means that you can conclude A implies B. So what happens here is to prove an implication, you assume what's on the left, right? You assume A, you do a couple steps, you get B out of the deal, and that allows you to conclude that, yes, A implies B. Okay? So this is called arrow introduction. Okay. Now what about a biconditional? Because we have that two-sided arrow too, right? To prove a biconditional, it's pretty much the exact same thing, but we need to do a little bit more work, okay? So let's say we're trying to prove A double arrow B. What we have to do is assume A. We do a couple steps, we get B. Great, this proves, just like we just talked about, right, that A implies B. But if we want to show that the arrow goes both ways, we have to do the same thing, but the other way around. So then we gotta assume B, and there's a break right here between the subproofs. We then got to assume B, do a couple steps, and get A. And this would be a proof that B implies A, right? You can see that it's just this thing, but now I'm showing that B is the thing leading to A, right? Not the other way around. Once I do both of these, I can write myself that A and B imply each other with that double arrow. And this is called biconditional introduction. Okay, a couple more. The last things we have are the negation rules. And these are probably the most difficult rules to learn when you're learning logic for the first time. They involve what's called a proof by contradiction, so they work the exact same way, but they can be a little tricky. So let's say you're trying to prove a sentence A. We could do this through any of the rules that we just learned, right? Like we could use and elimination, maybe arrow elimination. Eventually it gets us to the sentence A. But there's another way to prove the sentence A. And how you do that is you can assume the opposite of A. You can assume the negation of A. And notice there's another subproof running here because I'm making an assumption, right? So then if you assume the opposite of A and you end up with a contradiction in here, that tells you that there must have been something wrong with the assumption of not A. It led you into something logically impossible. And so on this basis, you can conclude A. You can take the negation off this guy and conclude the opposite of what you assumed. The argument is that, okay, I'm trying to prove A, so what if A is not true? That leads to a contradiction. Okay, then A must be true. Another way to look at it is it's showing that A is not allowed to be false. Because if it's false, you get something logically impossible. Now, what would a contradiction look like in a subproof? Well, it's going to look like this, okay? You're going to have some sentence here. It doesn't matter what it is. And then right next to that, you're going to have the negation of that sentence. So you're going to get like sentence right here, and then it's negation. But a sentence can't be true and false at the same time, right? So this is what your contradiction is going to look like. This is what your contradiction is going to look like, is a sentence with its negation. And this particular thing is called negation elimination. It's called this because we started with a negation and then it went away down here. So we eliminated a negation. There's one called negation introduction that works the exact same way. So let's say I'm trying to prove not A. I'm trying to prove that A is false. What you can do is assume A. Again, you assume the opposite of what you're trying to prove. You do a couple steps here, you get yourself a contradiction, and that tells you that A must be false. So it's the exact same reasoning as negation elimination, except it just depends what you're doing with that sentence at the very end. Are you adding a negation to it? Are you taking one off? You can do both, and they work the exact same way. Because we introduced a new negation in here, we call this negation introduction. But in both cases, the same thing happens. You assume the opposite of what you're trying to prove. You assume the opposite of what you're trying to prove, you show that there's something wrong with that, which means a contradiction, right? And that lets you conclude what you're trying to prove. Hopefully this will become more clear as we do examples. But these are two very important rules, and they're both called proof by contradiction. Proof by contradiction. So I might refer to them this way as we're doing examples. Negation introduction, negation elimination, both kinds of proof by contradiction, okay? Last but not least, there's a reiteration rule. And this one is kind of funny. If you have a sentence A, guess what? Later on in your proof, you can just write A again. You can write the same sentence twice. That's what reiteration tells you. Okay? So it's really a rule that's kind of not a rule at the same time. It just allows you to repeat yourself within a proof. Okay, so make sure you have all these written down. I recommend putting them all on a sheet of paper so you have them all in front of you and you can look at them all at once to try to figure out where you're going in the proof. So we're going to try a couple problems now. I'm going to write the problem down, and then I encourage you to pause the video at any stage after I write it down, see where you can get. And then once you're done with that, try to resume. Maybe you'll get a couple steps from me. You want to pause it again, try to get further on your own. That's how you end up learning this stuff, okay? So here's one problem that we're going to do. Here's some premises here. We got K, and we're going to have K implies L. And we're going to have K implies M. And then we're going to have, even more, L and M implies O. And then we want to prove O from these premises, okay? So pause the video 1 second, take a look at your premises, and see if you can get any information out of these using the rules you just wrote down. Okay, so here's how we're going to move forward in this thing. You want to look at the premises and figure out what information you can get out, right? So let's think about arrow elimination. This is how our rule was stated for arrow elimination, right? You have a sentence A arrow B, you get A, so you know B, right? This is normal arrow elimination. So if you look at sentences 1 and 2, this is exactly a case of this, right? You have K, and you know that K implies L. So guess what? I can go down here and just write L. And then over here, I want to put a reason. The reason that I know L to be true at this point is because of lines 1 and 2 and the arrow elimination rule, okay? So I'm going to cite arrow elimination. That's my rule right there. And I'm going to say which lines allow me to come to that conclusion, okay? So I know L because K is true and K implies L. Now you might also notice that the exact same thing is going on with M, right? You got K and K implies M as well. So I can go writing M down now for the exact same reason I knew L, right? This is going to be arrow elimination, but this time I use lines 1 and 3, right? 1 and 3 like this. Okay, so now we want to know what's going to get us to this sentence here. That's what we're trying to prove, right? So we look through our premises. What sentence involves O? Well, it's this one right here, right? So you can think to yourself, how am I going to get O? We've used arrow elimination a couple times already here, right? So maybe this is an arrow statement as its main connective. Maybe we could use arrow elimination to get ourselves O. What would we need for that? We would need this first sentence to be true, right? So then we can ask, okay, well, is this first sentence true? We don't have it written down yet, but we can make it true by looking at lines 5 and 6. I've proven L and M separately, right? So that lets me stick them together with an and symbol. Okay, if you're looking at that paper full of rules that hopefully you have written down, this is just our and introduction rule, right? If you have two sentences separately, you can put them together with an and symbol. And so I'm going to cite and introduction, lines 5 and 6, because that's where I got those two sentences from, right? Now, why did I do that? Because it's the left-hand side of this arrow in line 4. So now I can say L and M implies O, and now I know the sentence L and M to be true. So now I know O is true. Why? Because of this and arrow elimination. So this is going to be 4 and 7. So sometimes it takes a little bit of time to realize that these rules can apply to any sentence. It doesn't matter how big the sentence is, it doesn't matter how small the sentence is. Here I used arrow elimination with just these simple K and L and M sentences, right? But here I used it where the left side of the arrow was something more complex, right? It was this long sentence, L and M. And using 4 and 7 to do arrow elimination is a perfectly legitimate way to use the arrow elimination rule, not this one, but the arrow elimination rule, because you have the left-hand side of the arrow written down, okay? All right. Now we're going to try another one. Okay, so for this one, we're going to have F, and we're going to have G, and we're going to have G and F implies K, and we're going to have K or L implies M, and then we want to prove M. Okay. So we're going to hit this with a similar strategy that we did the last one. We're going to look at our premises here, and we're going to see how we can use the rules to try to squeeze out information from these premises, okay? Now maybe you're remembering the last problem. This kind of looks a little bit like that, right? We could use this sentence to get to K if G and F were both true. Then we could use arrow elimination, just like we did in the last problem, right? And this right here is our connection to M, right? This is our only connection to M in the premises. So probably we're going to want to use arrow elimination in a series in lines 3 and 4 here to get to K. And then here's where K is involved. And then we're going to get to M somehow. So that's what you can think when seeing this problem. Pause the video for a second if you haven't already. Give this thing a try. And yeah, good luck. Okay, so how we can do this, we see that the sentence G and F is involved here, right? G and F. I get them separately right there, right? So I can just stick them together with an and symbol. That's and introduction from 1 and 2, right? I get both sentences separately, so I can put them together like this. Now, this sentence implies K, right? That's what line 3 tells me, is that this sentence right here, there it is, that thing implies K. So now you can write K. And that's going to be arrow elimination, just like on the last problem, right? 3 and 5. Okay. Now how are we going to get to M? We got line 4, right? That gives us a connection to M, and we have K written down. We could get to M if we used arrow elimination on the sentence K or L. So now we can ask ourselves, is the sentence K or L true based on what we know? And this is where or introduction can get tricky to learn. This sentence is true because I already have the sentence K written down, right? So the or introduction rule lets me put whatever other sentence I want with K. If this seems weird, look real quick at your or introduction rule. If you know this sentence is true, this sentence must be true as well because it only needs one of them to be true, right? It only needs K to be true. So I can hit line 6 with an or introduction, K or L. And notice how there's just one line cited here, right? Because I only needed one sentence to come to this conclusion right here. I only needed the sentence K to know that K or L was true. Why do we care about that? Well, because it's the left-hand side of this arrow right here, right? So because I know that this implies M, and this is now true, now I know that M is true. By arrow elimination on 4 and 7. K or L implies M. I know K or L to be true now, therefore I know M is true. And that is the thing we wanted to prove. Okay, we're going to do 2 more. So this one, we're going to get R, and we're going to get T, and we're going to get R implies S, and we also know Q, and this one's kind of long, Q if and only if R implies S and T. And we want to prove Q and R. Okay. If you haven't already, pause the video, see if you can work this guy out. Yeah. Okay, So if we look at what we're trying to prove, it's an and statement, right? We're trying to prove Q and R. So it's kind of like we're trying to prove that two things are true, right? Q, like we're trying to prove that Q is true, and, because this is an and symbol, we're trying to prove that R is true. One of those we have as a premise, right? So that's cool. We already have R on our hands. So now we only have to pretty much worry about getting Q. This right here is our connection to Q, right? And Q is implied, it goes both ways here in this biconditional, right? Q is implied by this guy, this long guy right here, right? So, if we can figure out that this guy is true, then that will imply Q. Remember that your biconditional elimination rule is like this, right? If you have A double arrow B, and you find that one side of that arrow is true, the other side of that double arrow must be true as well. Biconditionals let you go both ways like this, unlike the normal conditional like this guy. Okay? So that's kind of our strategy to get Q, is we're going to try to see if we can deal with this sentence right here. Okay, so this turns out to be easier than it looks. This right here is an and statement, right? It's an and statement between two sentences. R arrow S, that's its own sentence. And this and symbol connects that sentence to T. So all I have to do to construct this sort of long, scary looking sentence is take these two guys and put them together with an and symbol. That's all I have to do. So this will go like R arrow S and T. And I knew that was true because both of these sentences individually are true, right? This is line 3 and this is line 2. So I can just go ahead and put them together with an and symbol, right? Nothing wrong with that. So this is and introduction from lines 2 and 3. Why did I do that? Well, because this sentence right here implies Q, right? So all I have to do now is write Q, because I know that this thing is true, and line 4 tells me that this thing implies Q, right? So you write Q, and you'll remember your rule for that was biconditional elimination from lines 4 and 5. This is an example of how those sentences A and B and the rules I gave you can really be anything you want. It can be this long sentence, R arrow S and T, right? It doesn't need to be something short. This whole thing implies Q. So if you can write that whole thing down, you can write Q down as well. So it turns out to be a little bit more straightforward than maybe it looks. Okay, last one. And this one's going to be kind of interesting, but it's a fun example of how you can kind of use the rules to do things that shouldn't make sense, but they do. So we're going to have one premise, X and not X, and we're going to try to prove Z if and only if P or Q implies X. Okay. So you might look at the sentence we're trying to prove and think, how on earth do I prove something this long? Think about the premise it gives you for a little bit, see what you can do, and pause the video, give it a shot, and then come back and I'll give you the answer. Okay, so as it turns out, we're not going to go constructing this entire thing in a proof. Or, well, we are, but it's going to be shortcut a little bit. So this premise right here, you might recognize is a little bit funny looking, right? It's telling you that X is true, and it's also telling you that not X is true. This is a contradiction, right? It was what I was talking about earlier in those negation rules, right? This is like a contradiction. It's saying X is both true and false. So I can do something funny with it now. This is an and symbol, right? So and elimination, you can check your and elimination rule. This lets me write down X and elimination on 1, right? This tells me X and not X, so I can pull X out of this and statement just by using and elimination on line 1, and I can do the exact same thing with this guy, not X, okay? And elimination on 1. Check your and elimination rule, this guy. Make sure it all makes sense so far. Okay, now I'm going to pull a trick here, okay? I'm going to take line 2, and I'm going to use or introduction on it. Remember that if you have this sentence X, you can add any other sentence you want with an or symbol, right? This is what or introduction allows us to do. So, when I try introducing another sentence with the sentence X, why don't I try this entire conclusion sentence right here? Why don't I try this whole thing? Like this. This is a good use of or introduction from line 2. Why? Because if you look at this big long thing, it's just an or statement, right? It says X or big sentence, right? And I already know X is true, right? So this guy is true. This guy, we have no idea what's going on with it, right? But the or symbol only cares that one of them is true, right? So this whole or statement is true just because X is, right? So again, I used or introduction here in kind of a tricky way. I put X with this huge complicated sentence. But now, I can't erase that, I guess. Now, go and check your or elimination rule. Or elimination lets you do this, right? You have an or statement, you figure out one of them is false, that means the other one must be true, right? And because this premise is so weird, right? It's a contradiction. This guy tells me X is false, right? So now I can just use or elimination on lines 3 and 4. I can reason like this. Here's 2 sentences. I've proven this one. Line 3 tells me this guy must be false. And so because this or statement is true, the other one must be true. So I can go down here and just write my conclusion. You just make this or statement. You say, hey, line 3 says that this one is false. So apply or elimination right here, and this other sentence on the right must be true. And that's our conclusion right there, right? Now maybe you noticed about this thing, there's nothing special about this sentence right here. I just kind of built this so that it was kind of scary looking, and you maybe would be surprised by this result. But the point is that you can prove anything you want from a contradiction. Maybe you remember this from early in the semester. Put a contradiction into your premises, you can make an argument for anything. This is how this shows up in the proof symbol system, is you can use or elimination here in a tricky way to prove essentially whatever you want. So that's kind of a fun application of this rule. And yeah, next time we will, or in the next video, we will cover assumptions, specifically with conditional proofs. Okay, so hopefully this gave you a taste of sort of applying the basic rules for a few simple problems. And then next time we're going to take things up a little step by starting to make assumptions and proving conditional statements.